Hello everyone, this is Oshini from Cheenta. Today I want to share with you a little bit about the research that I do, and some of that also goes on to the research projects at Cheenta. I work in a field called geometric group theory. Let me write that down. It's a very beautiful subject in mathematics. It's called geometric group theory. So, the word group, let's look at that first, because if you are working on Mathematical Olympiads or ISI-CMI Entrances or Physics Olympiads, even Computer Science Olympiads, you may have seen a group. Well, it is not taught at the school level for sure, but I have said this repeatedly. It always helps if you have a bird's eye view of what is happening. Groups are everywhere. They are essentially sets of symmetries. And since symmetries are everywhere, therefore groups are everywhere. When some object is symmetric in nature, it's pleasant to your eyes. It looks beautiful. And that's where groups come in. Now, what is a symmetry, you may ask? So, this idea actually stems from geometry. So, let me explain what is a symmetry. A symmetry is a motion. At the moment, let's think about it like that. A symmetry is a motion, and if you move objects in that motion, you cannot tell the difference before and after the motion. You cannot tell the difference. So it will look exactly the same before and after the motion. So, let me give you an example. Suppose you have a square. Now, if you move the square about the intersection point of the diagonals, if you move the square about the intersection point of the diagonals by 90 degree, that is, rotate the square by 90 degree about the intersection points of the diagonals, then what happens is this point goes here, this point goes here, this point goes here, and this point goes here. If I have not labeled the vertices, that is, I have not written A, B, C, D like this. If I have not labeled the vertices, then you won't be able to tell that there is a rotation. Rotation by 90 degree brings the square back to its own position. Therefore, rotation by 90 degree about the point of intersection of the diagonals of the square is an example of a symmetry. So, here is a challenge question. Can you write down all the symmetries of the square in the comment section? And here is a little bit of hint. Not all of them are rotations. So think about it. Can you write down all the symmetries of the square in the comment section? As opposed to 90 degree, if you rotated it by 45 degree, the square would look somewhat like this. Right? After rotation, it would look somewhat like that. and you would immediately know that there is a movement, there is a motion. If you looked at the square before and if you look at the square afterward, you will be able to see, okay, there is a difference in the location of the square. So yes, rotation by 45 degree is not a symmetry, not a symmetry of the square. Okay, so students, I want to tell you something very interesting here. Whenever I learn a concept, I look for examples and I look for non-examples or counter examples. Once I understand an example and a counter example, the underlying concept becomes very clear to me. So you can try this experiment with yourself as well. Whenever you learn something new, look for an example and a non-example or a counter example. Okay, so coming back to this notion of geometric group theory, now we know, at least vaguely, a little bit, what is a group. A group is a collection of symmetry, set of symmetry, of some object, set of symmetries of some object. Now there comes the fun part. Look at the word object. Sometimes you are just handed out with the group. You do not have any idea what object is underlying this. What group? Okay, so the set will have certain properties. If the set has those properties, it is a group. But the question is, what objects' symmetries are we looking at? Sometimes that object is not very clear. We don't know. For example, I'll give you an example of a group. 1, 3, 5, 7. This set of numbers represents a group. How do I know that? Well, that's a different story. I have to check certain properties. So just by telling you the set, it's not enough. I have to also tell you an operation. What kind of operation I can use to combine elements of this particular set. So I have to look for the operation. And once I have the set and the operation and all the properties are satisfied, I have a group. So I'm not going to say what the operation is at the moment, but just by looking at the set 1, 3, 5 and 7, it's very hard to tell we are looking at which object's symmetries. Turns out, if you can figure out an object whose symmetries you are looking at, if you can figure this out, and there might not be a unique object, there can be many types of objects having the same type of symmetry. So if you are looking at an object, if you can figure out which object you are, symmetries of which object you are studying, then the geometry of that object, has a lot of good information about the group itself. Think about it. I have reversed the question. Now, instead of starting with an object and looking at its symmetries, I have started with an abstract group which contains a bunch of elements, and we have no idea whose symmetries we are looking at. And then we try to figure out that object whose symmetries we are looking at, and then we study the geometry of that object with the hope that the geometry of that object will reveal more information about the group. This is a very interesting way of looking at symmetries in an abstract way. Okay, and geometric group theory is very deeply related to something called hyperbolic geometry. Hyperbolic geometry. Maybe in some other video I will talk to you about this. Several students at Cheenta have done projects on hyperbolic geometry, geometric group theory. School students have done it, college, university students have done it. And it's a very active field of research. You can check the link in the description if you want to look at some of the work that we have done so far. What we believe is that if you are preparing for the Olympiads or if you are preparing for ISI-CMI entrances, then you already have a knack, an inclination to figure out the unknown. And much of mathematics is unknown. No one knows the answers to many questions. These are called open questions. And won't it be great? Won't it be absolutely thrilling if we could together make a little contribution toward those open questions? It's really hard, but it can be a life's work. Okay, so I encourage all of you to explore research. It is perhaps the most noble pursuit that a human being can take up. And I'm sure that you're also learning great mathematics, physics, computer science, statistics, because these are the tools that we use at Cheenta to learn and figure out new things. Okay? All right. Thank you for joining in today. I'll see you in the next one, and keep on doing good mathematics.